Standard data organization typically relies on continuous geometry. We map information using metric distances and calculate similarity scores to force data points into clusters. Formal concept analysis operates on a different premise. It discards metrics and probabilities to ask an austere question. Given only which objects possess which attributes, what logical dependencies are strictly determined by that pure incidence alone? Formal concept analysis computes exact algebraically closed sets, distinguishing its output from the similarity-based groupings of hierarchical clustering. We will construct this system from first principles, moving from a raw incidence relation through an Antitone-Galois connection to build both a concept lattice and a formal logic of dependencies. Understanding this construction allows us to move beyond statistical heuristics and into mathematically auditable certainty. The foundational axiom is a binary data table, formalized as a context K equals G, M, I. Here, G is a set of objects, M is a set of attributes, and I is the binary relation between them. We define a derivation map for objects, A'. By selecting a specific set of objects, we isolate the strict set of attributes that every member of that set shares. The same operation applies to attributes, B'. Selecting a set of attributes isolates the precise set of objects possessing all of them. These maps are linked by an Antitone-Galois connection. This means that every object in set A has every attribute in set B, if and only if every attribute in B is possessed by every object in A. These maps reverse inclusion. As you increase the number of objects in your selection, the number of shared properties they can all maintain must shrink. This back-and-forth mechanism serves as the engine for discovering exact empirical indiscernibility in any dataset. Composing these operators, applying the derivation map twice, creates a closure. We take a set of objects, find their shared attributes, and then find every other object that also shares those attributes. The set expands until it hits a stable limit. This closure operator is extensive, it is mathematically monotone, and strictly idempotent. Applying it a third or fourth time will never change the result. It has reached a fixed point. Closure defines two things: empirically indiscernible objects on one side, and strictly forced attribute dependencies on the other. When an object set and an attribute set are mutually closed, they form a formal concept. The objects are the extension, and the attributes are the intension. This mathematically formalizes the classical duality of a concept, a collection of things falling under a definition, and the collection of marks characterizing those things. We order these formal concepts by the inclusion of their extents. This naturally forces a reverse inclusion of their intents. This creates a hierarchy where lower concepts are more specific, covering fewer objects but asserting more attributes, while higher concepts cover more objects with fewer shared marks. The basic theorem of FCA states that the collection of all these concepts forms a complete lattice. Every pair of concepts has a unique supremum and infimum within the order. Navigating this structure requires two operations, meet and join, which possess an asymmetrical mathematical architecture. The meet operation is straightforward. The intersection of two closed object sets is always closed. We move down the lattice to find the most general concept that both share. The join operation requires the closure operator. Simply combining two object sets usually results in a non-closed set, which must be expanded to the least closed generalization above them. The concept lattice represents the completed algebraic order inherently hidden within the raw incidence data. The same closure operators that build the object hierarchy also generate a theory of attribute dependencies. We express these dependencies through the implication formula. X implies Y if the closure of X contains Y. This is a strict rule. It states that every object in our context that possesses the attributes in X is guaranteed to possess the attributes in Y. In large datasets, the number of valid implications can be unmanageable. Finding every possible rule becomes computationally impossible. We solve this using the Duquenne-Guigues basis. It identifies a minimum set of implications from which all other valid rules can be derived, providing a compressed axiomatization of the data.
This maps order theory directly into propositional logic, extracting a minimal set of horn-like rules from the initial matrix. Real-world data is rarely a simple binary table. Objects are often described by numerical intervals, trajectories, or complex graphs. Pattern structures generalize the framework to handle these structured values. By replacing binary incidence with a meet-cena lattice of descriptions, we preserve the closure architecture for non-binary data. This bridge allows us to apply the rigors of FCA to the continuous outputs of machine learning models. By binarizing neural representations, mapping high-dimensional activations to discrete features, we can construct a formal context from latent weights. Because the closure operator identifies stable conjunctions across the training data, we can finally test whether a model has developed an emergent conceptual structure. This enables attribute exploration with an LLM acting as an oracle. The model proposes dependencies, while the framework demands counterexamples, creating an auditable neurosymbolic loop. The future of explainable AI depends on imposing these exact boundaries on continuous statistical data. The core of the field is a four-stage transformation, from incidence to connection, from connection to closure, and from closure to the dual output of lattices and implications. This is the guaranteed passage from raw data to an explicit theory of dependency. We must remember that FCA separates preservation from selection. The mathematics guarantees the internal structure, but the human analyst remains responsible for defining which attributes are meaningful. As we generate more uncertain and distributed data, the ability to rigorously test which conjunctions are stable is essential. Formal concept analysis provides the mathematical bridge necessary to make modern reasoning explicitly auditable.